Hello friends, in last lecture we see definition of lattice and complete lattice. In this lecture we are going to study some examples of lattice and complete lattice. Here first P is a chain, then P is a lattice. XY belongs to P. P is a chain. Then here X join Y is equal to maximum of XY and X meet Y is equal to minimum of X and Y. That means every pair meet and join exist in chain because every pair is comparable, X comparable to Y, that means X related to Y or Y related to X, then X meet Y or and X join Y exists. And so every chain is a lattice. Here real numbers, rational, real rational J are lattice. Under usual order, under usual order, set of natural number is also a lattice. Is also lattice. But these are not complete lattice. These are lattice because R, Q, Z, N are chains and every chain is a lattice, and so it is, these are lattices. These are example of that, but not a complete lattice because complete lattice have top and bottom element. Top and bottom element. Here R as a no top element, also Q as a no top element, Z also no top element, N set of natural number is also no top element. So these are not complete lattice. These are not complete lattice. Here X comma Y belongs to R. X comma Y belongs to R and X strictly less than Y. Then close interval XY is a complete lattice. Is a complete lattice. Here top and bottom exist, so it is complete lattice. Now second example here, let X be any set and P of X is an order set, complete lattice. Here, suppose here is a set and it contains AI such that AI is a subset of X and S is a subset of P of X. Then join of S means union of this all AI. I belongs to I, like this. And meet of S, intersection of AI, I belongs to I. Join yes and meet yes exist for each yes. Join yes and meet yes exist for each yes subset of P of X. Subset of P of X. And so it is complete lattice. Now, this is lattice. Let L is a lattice and this is subset of P of X, then L is known as lattice of set. Then L is known as lattice of set if it is closed under finite union and intersection. And it is complete lattice. If it is closed under arbitrary union and intersection. Here, this is lattice. Power set of X is lattice and it is complete lattice. Now, L is a subset of P of X. L is a subset of P of X and this is called known as lattice of set. If it is closed under finite union and intersection, and it is complete lattice if it is closed under arbitrary union and intersections. Arbitrary union and intersections. Here, now, next example here, the order set Mn, n is greater than equal to 1 is a lattice. Here, this is M2. This is M3 and so on like this. XY belongs to Mn. XY belongs to Mn. Okay, with X parallel to Y means X, Y in anti-chain belongs to anti-chain. XY, XY are in the anti-chain. Let me like this, X, Y, X, Y. Then X join Y, then X join Y is equal to top and X meet Y is equal to bottom. X join Y is equal to top and X meet Y is equal to bottom. And so it is lattice. It is lattice. And clearly it is complete lattice. Clearly it is complete lattice. Now, here another example. Fifth, here N0 with this relation, that means division, N0 set of non-negative natural number. N0 is set of non-zero, and here this relation means n related to m if and only if n divides m. N divides m. Here x, y belongs to N0. X join y is equal to LCM, least common multiple of m and n. And x meet y is equal to GCD of m and n. If division relation, then join defined by this way, x join y is equal to LCM and x meet y is equal to GCD, then every two integers, non-negative integers, have a LCM exists, also GCD exists, and so it is lattice. So therefore, in N0 is lattice. Is it? lattices of subgroup. G is a group. Sub G, set of all subgroups of G. Set of all subgroups of G. Sub G under inclusion is an order set. Is an order set. Here H and K are subgroups. Here H and K are subgroups of G. Then H meet K is equal to H intersection K, and H intersection K is again a subgroup. H intersection K is again a subgroup. Now here, but H union K may not be subgroup. May not be subgroup. H union, then how to define H join K? If H and K are normal subgroups, then HK, define HK. HK, H belongs to H, small k belongs to capital K, is a subgroup. Is a subgroup. And then H join K is equal to HK if H and K are normal subgroup. Normal subgroup. Now, if we take N sub G, that means set of normal subgroups of G. If we take N sub G, set of a normal subgroup of G, then N sub G is a lattice. Is a lattice, and defined by this here, H join K is equal to HK and H meet K is equal to H intersection K. H intersection K. Okay, so we stop here. Thank you.